Hello, good morning. Thank you all for coming to my talk, Practical Machine Learning for the Games Industry. Let me introduce myself first. I'm Christian Peter Heimbach. I am 18 years in the industry. I had the pleasure to work across all major brands and platforms, but also I made a shift in my career. I started on the business and publishing side of games first, and then 8 years ago decided to change sides and go into engineering and coding. Since then, I founded a company called Tech. We are integrating the web and game microservices, so from simple websites to fully integrated pages into live games. So, yeah, today's talk. We're going to talk about in major two chapters. The first one is the basics of machine learning and how to apply machine learning later. So I give you a bit of context of why this talk, what motivates me in the topic. We're going to look a bit under the hood of what happens in machine learning models and then do a bit of a deeper dive in GPT models. And then later when applying, I want to give you the tools at hand of where would you find models, how could you use them in a specific technology currently called RAGs, the Retrieval Augmented Generation, and some more strategies. Cool. So first of all, you might ask yourself why, right? We're talking about AI machine learning for a while. And I asked myself the same, obviously. And I had this experience, like many of you probably played a bit around with GPT, saw impressive demos, but in the end of the day, so what? What can I do with this, right? Is this something that makes sense? Can I use it? And the next bit is, what can I have a share in this, right? Is there open source tools? Open source for my career has changed everything. So I wanted to know, am I only here using it like Google? Do I have to use big text provisioned tools, or can I have my own? And then last but not least, fun and profit. I love learning. We're engineers. We enjoy the new thing to have a look what can be done with it. And obviously, we want to grow our companies. So that is what motivated me. The next thing you might ask is, am I in the right room? Obviously, machine learning is nothing completely new. It's even around since the 60s. Some people in our industries use it on quite an expert level already in the analytical sphere. Here today, I want to focus for the people like me that maybe not the complete starters, but that come in, want to now see, okay, what can I do with it? And a bit more on the generative side of AI versus analytics. If you're an expert in analytics, please share your opinions later after the talk. I'd love to hear your ideas. So machine learning is still has still a growing industry attention. Our friends from ECO provided us some coverage data. It doesn't show any slowdown, quite the opposite. The article amount is growing and has bursts whenever there is a new technology coming along. So it is worth keep paying attention here. But before I dive in, let's also speak about some important elements around ethics and the general philosophy of using machine learning. And I have a favorite tweet here from Joanna that I'll let you read, which is basically, yeah, let us not make AI take away what we enjoy, which is art and the craft, and let us use it to tackle our chores. And besides that, another big topic, obviously, is data ethics. Right? In our industry, it's not as big a problem as, for example, in health or in military applications, but nevertheless, we should have an eye on how do we apply this tech and what does it do to people, right? People wrongfully accused of fraud, etc., can cause distress also in games. Then legal advice is important. Yeah, we know that this is a new field, so there might be still some areas we need to pay attention that, we're not violating the law. And then last but not least, I also urge you, as programmers, let us leave AI and ML not to the lawyers and to the big tech alone. Have a look at what this tech can do. Let us play and tinker and see how we can make better games with it. So let's talk about the basics of machine learning and what would be a better way to do this, to just dive in straight away. And I need to do this with a small example. So I took this from a course of Fast AI, which I can highly recommend for everyone interested. I'm running this here in an environment called Jupyter Notebooks. You might have heard of that, but it is basically a combination of code and document. It's kind of the lingua franca. And I show an example that I call a Hello World example of is it a bird or not? And basically what we're doing is we're downloading images from DuckDuckGo. And we will later identify whether the picture is a bird or not, or a forest, sorry. And so what I'm doing here is just call this function, and I've run this earlier, just excuse me, I don't do it live because we don't want to trust the hotel internet too much. But basically, we have a bird image, I download a forest image, and then we download more training data, which basically is we're looping a bit over forest or bird, we give it a bit of variation so that our training data set is rich enough in variety so that we have the ability to look at various different birds. And I also want to mention that nowadays we can fine-tune models with far less training data than you might imagine. So here we're talking about 400 images, so it's not much. So then we filter some broken images out, and then I'm using a data loader. That's a simple Python object that basically looks at what is our data. It gives each image a label. It resizes them accordingly, and it prepares the data into a validation set and into a training set. And then basically what can happen is now we can feed this into a model. Here I use ResNet, which is an image model that is suitable for CPUs. Again, what you see here, you can see the timings under these blocks. This goes all very quickly, and it's just a CPU. So if you run this in a proper environment, the machine learns over this data. And now, fingers crossed, we can use the model. So we're using our original bird and check if the model can understand what we're looking at. Yes, it does. This is a bird. Hooray, it has worked. But obviously, let's have a look if it also works with the forest. Sorry, I need to do this here in a weird angle. Boom, it understood that as well. So you see here in a very few clicks, in a very few lines of code, we basically have already a classification model working quite well for us. Obviously, we are engineers, so let's try and break it. What happens if it looks at me? Oh. Running. Okay, accordingly, I'm a bird. So what has happened, obviously, when we're running models, we need to be aware that what we train for is also what we get out. This model only knows of forest and birds. So luckily, I'm looking a bit more like a bird than a forest, but here we are. So let me get my mouse back. And we can continue. So let's look under the hood what I have actually done here and what is happening in these models. So let me start with some first principles of the differentiality between computer programs as we know them and machine learning models. A computer program, we all know, it takes inputs, it has an instruction set made by humans that then does a computation on these inputs and creates a result. Machine learning models work slightly different because you give not only inputs into the model, you will also give it weights. These weights are trained on instructing the model how to process the inputs to predict a result that we would expect. And that is fundamentally different because you wonder where do these weights come from? And they come from basically starting a machine learning model with completely randomized weights. Then you run your inputs with these. That's what we did during the training example. And then we compare the performance. And is the performance, the error rate of does it do the right job or not, is it correct or not? And then we adjust the weights. And we're looping over this process so long until we have a result. And I have, again, prepared something to visualize this in a technology that you should be aware of, which is the stochastic gradient descent. And this all sounds very fancy. But basically what we're doing is, imagine we have a quadratic function, and just imagine we had a data situation that shows us here these dots. Yeah, and what the machine is basically trying to achieve is, it tries to adjust these parameters or weights to try and match these points here. Yeah, and obviously you can see if I'm fiddling there, we can do that as humans quite visually, but the machine needs a value to optimize against. And it uses this so-called loss function. In our case here, this is a mean square error. You might remember that from school. This is ultimately the squared distance of all the points to the graph. And so now what we can do is we can have a look here and fiddle, and we can try and get this value lower and lower this is by 120. What happens if I do this? Oh, it's getting higher. So yeah, you see me. This is exciting. Who wants to come to game night to me? But so yeah, if I did this 340 billion times, you can imagine that's about the weight that the modern model needs to perform. But obviously the machine now can optimize this. Another word you should be aware of are gradients. Gradients are basically the impact of each of the small variations of these levers I just showed you, these parameters, on the loss rate. So you can see here, so imagine there would be a little label on them, and you can see A has the highest impact on getting the loss rate down, which is what we want, a little bit on B, and then again C. So once we have this, the machine can automate this process. And here's one of the biggest important hyperparameters when working with machine learning models, and that is the learning rate. It is here, this small value that tells us how to adjust these gradients, how small are the increments of the changes we want to make. And so then when we make the machine run this, you can see now the machine with enough iterations can bring the loss rate down by its own. And this is ultimately, in the big picture, what is happening across all the machine learning as we know it. Good. So the next topic we need to talk about is the learning loop that I showed you, but also the overfitting risk. So what happens easily when we are having a machine learning model work is we still need experts to understand, has the model overfitted? For example, if we're driving this too far, you can see that this model now is very good. It hits every point, but it cannot predict anything anymore outside of the data it had been learning, right? So it would basically be a broken model. Now you would ask me, hey, this doesn't look any more quadratic. And obviously the world isn't only quadratic, so how does it really work to be able to create any function? And for that, we need to go and delve a bit into why do we use this word neural on neural networks. And the idea is that it is modeled following our human neurons, our brain neurons, which are, and I don't want to pretend to know too much about biology, but basically when a neuron gets activated by its connections, what it then does is it has a certain threshold. When this is hit, it activates follow-on neurons. And in machine learning, we're doing this with an activation function, and a popular one is called the ReLU, or the rectified linear unit, which basically looks quite unspectacular. You can see this here. What this function ultimately does is when it gets a value smaller or equal 0, it returns 0. If it gets a higher value, it will activate this so-called slope function, which ultimately enables us to give a value back to its following neurons. That itself is not so spectacular, but what blew my mind when learning all this was that now if you connect all these slope functions and you have enough parameters, you can basically create any function. Any function can be displayed as long as you have enough parameters, enough data to train it. It can model this against all known functions. So now, if you connect enough of them, what happens is basically you have a neural network. Yeah? You can have now these different mathematical operations running in parallel and in these layers, sorry, and then you get a prediction accordingly. When you have more than 3 layers, that's when people call it a deep neural network. Yeah? Let me get a quick drink. So getting into the wider conversation, we often hear that deep learning layers are a black box, right? People complain, we don't really know anymore what happens in AI networks, but that's not necessarily true, and there was a great paper that shows of how convolutional neural networks are processing data internally, and I want to show this to you because it's quite visual and helpful for us humans to grasp. So if you look at the first layer, what it does is when looking at imagery and image classification, it identifies very basic things, slopes, colors, right? The very basic of images. Then you see in the next layer, these forms and patterns, they get a bit more complex. We see now corners emerge, we see circles, right? And this process continues, it gets further complex. So now you can see it can detect faces, it can see the rims of cars. So the model gets more and more capable to understand different categories of its neuron activating. And here we are now with bird feet, different dog faces, that continues. Now you can see dog races. You can decide, you can see gender, etc., right? So the model over layer of layer of layer gets more and more capability. Some two foundational words that are very important in all this field is fine-tuning and transfer learning. So obviously training a model from scratch is quite expensive and time-intensive and compute resource intensive. So what we're actually doing when often speaking about training, we are fine-tuning. That means we just replace the last layer of the network with the information we care about. So for example, we have this image network. It understands already how images work, what are aspects of an image. And then we just changed the last layer, for example, to categorize between birds and forest so that Christian looks like a bird. Then the other big topic is transfer learning. So a big idea here is that you don't have to stick with a model that is maybe trained for images to just categorize images. So for example, here people have used image networks to detect fraud. Someone visualized the click flow of users and could that compare with fraudsters. And then it was very quickly able to detect a fraudster without all the knowledge you would normally need from experts to create a true rule set of what makes a fraudster. Same here with malware. Someone made an image of the bytecode compiled and could detect malware using an image model without all the deep expert knowledge you would normally need to know how a malware is working, right? So that is very exciting stuff. So I hope that was all not too crazy, because now it gets crazy. So that is how do actually the new GPT models work, right? The generative pre-trained transformers is all the rage. This is what you hear when you see GPT-4, etc., doing all the magic they do. So let's talk about first where does this come from. And there was this groundbreaking paper in 2017 called "Attention is All You Need." Originally, the models were used to enable translations. And for translations, it's very important that the machine understands context, and that also this paper enabled a new model architecture that could be run in parallel. So first of all, these models can train without human-labeled data. That was another big bottleneck removed here. So the model would just be fed data where certain words are missing, and it would be trained against predicting the right words. And it excels at transfer learning. Plus, last but not least, it unlocked the big tech scalability, the Silicon Valley arms race, because the more compute you had at your hands, the more data you had, the better your models would perform. The architecture itself is split in two parts. There's the encoder and the decoder. The encoder is treating the prompt from the user. It will try and understand what is actually being said. You can also use it independently, for example, to get a sentiment classification from what people say. And then there's the decoder bit, which generates on the basis of the user's input. So that would be summarization, continue the sentence, right? Like the things that we use when we're using these modern chatbots. Obviously, this is all a bit more crazier under the hood, and so I won't take you there and only focus on what's important. So the first step when you use these models, what happens is a process called tokenization and embeddings. Basically, imagine we're typing in, the game was not so boring. It first needs to get tokenized so the machine can work with it. Tokenization means it gets broken down. Here in my example by words, and it adds a few more specific tokens to signal when there is a capitalized letter, when it's the start of the prompt, the end of the prompt, etc. But also, I show here a per word tokenization. It could also be in subwords. That's even crazier, but think of Asian languages, right, that are not necessarily be broken down by words. So once the machine has tokens, what it does is it matches them with so-called embeddings. Embeddings are vectors, again, a long list of weights, about 768 to even 3,000 dimensions in the most modern. And it tries to give now a value to each of these tokens that also reflect the position of the sentence. Now, this looks complete banana. Why do we do that? And to make sure why this happens, I need to explain the vector space, or how does a model even generate meaning and the understanding of how words are together in a space. So if you think about a three-dimensional vector space, I use this here just for simplification. Imagine we have a person and we want to speak about its biological gender. Say we have a man here, and then we have a specific vector operation to move from a man to a woman. Now, we can apply that same vector mechanics and vector calculation, for example, to apply to a noble. So now we can use the same spatial computation to get from king to queen. So suddenly the machine gets an understanding how in different contexts, different words create the same logic. Yeah, and we can do the same with their kids, son to daughter, and the kids of nobles, the prince and princess, right? So you see how now in this vector space, the machine is able to navigate meaning or an understanding of which words belong together. So obviously, that was not enough. This technology is as old as when Google started to try and measure how keywords are belonging together. So this is an older tech. What made this paper so special is, attention is all you need, is the so-called attention mechanism. And the idea here is that, of course, specific words have an impact on the meaning of the sentence. Like here, the game was not so boring. Obviously, we're not just talking about a boring game, not so boring game. So what the machine does is it makes a cross matrix to calculate the importance of different words on different other words. For example, for boring, the word game is very important and not, because it's not boring, right? And so you can see here this cross calculation of which words are very important to each other and which words can basically be omitted, right? Like, for example, the almost has no big meaning here. And this just not happens on a single matrix of weights. This happens a lot in parallel, and it was needed to do this in a lot of parallel operations at the same time to get more meaning out of the prompt and to create a better meaning when generating more copy. And let me visualize what that means. When we, for example, try and generate an image that speaks about a boring game or not so boring game, there needs to be a lot of different things addressed here, right? You see the different colors, you see the board looks different of that game, the people are obviously look a bit scarily funny there, right? So you see that a lot of different variables need to be impacted to create something as a believable output. And that parallelization is what I talked about earlier, where big tech can really play its muscle, right? If you have a lot of compute resources, you can operate all of that in parallel to create much better outcomes. So we all are aware as well of GPTs and machine learning models' common issues and gotchas. Hallucination, obviously a big one that has been talked about tons. You can mitigate this by the way you craft your prompts. You can also have user feedback there. That's very important because you will still need an expert to tell you that what came out there is not useful or useful. Another one is context length. That's a big topic at the moment because it's the key value that's getting improved at the moment by the industry. I think Google's latest model has 3 million tokens now you can put in. You saw this cross matrix earlier. You can see the compute effort goes up almost by square, right? Because you have to measure all the different prompts against each other. But be careful using too much context because that still is what defines time and the cost when you're using machine learning models. Last but not least, user expectations, right? We humans are very good at, once we see certain signals that reminds us of ourselves, we think we are there with a human, but it's not, right? So the model will still give you sometimes very bad results, or it, fools you how good it actually is. So always have in mind, you're using a machine and it is only probabilistic. Good. Chapter 2, machine learning. So first I want to talk about how we find and apply models. And the model selection or the model hub is the first point of contact, really. This is one of my favorites, Hugging Face. You can find a lot of open source models. You can see already models that the community has pre-trained, so it can save you a lot of time. Working with machine learning is a lot of iteration, so try a lot of cheap things first before you start and go into the time-intensive training procedures and so on. Yeah, try different things fast. And there is a surprising set of tools out there that I'm going to go about in a minute. Dev environments, yeah, you can set up your own Python environment. That's not for the faint-hearted. You can also use environments such as Colab that's prepared from Google. You can match them then also with cloud compute resources, so you can instantly start working here without all the tech headache. Then libraries. I urge you to use things like the Fast AI library or PyTorch that take a lot of the legwork out of splitting data sets, calling the right models in, etc. TensorFlow is the one most advanced, but yeah, have a look. These tools are out there, and then Kaggle is a good learning resource. I put it here just so you find some more resources. Then machine learning models are out there in a lot of variety. Yeah, for all the various use cases. I can't talk about them all in detail, but you'll be surprised how much is out there and how much specialist and already very capable models are at your fingertips. Great. So the next I want to talk about is more about how can you take machine learning models into a practical environment in your studios, in your companies. And what we're using here is a retrieval augmented generation. Obviously, this tries to address some of the shortcomings of large language models, which obviously only are being trained on public data, but you might need to use them in your internal data. And let me show you what that is. Basically, what a RAG allows you to do is it allows you to define a workflow of activity, and it allows you to bring your own data, as I said. So what you can do is you can use open source models. You can have them running in your own environment. You don't have to worry that some of your sensitive data leaves your environments. So it's very useful technology. You can also build observing into it. That means when your users are using it, you can see, does it throw errors? You can monitor it, right? So it's very helpful to overcome certain shortcomings. Let's have a quick look at the detail flow of a RAG. Basically, imagine what we're doing is we have a user that will interact with an app that can be as simple as a form. Then the prompt of the user goes into a retrieval model that consults with a vector database. The vector database basically includes all the embeddings of your own internal documentation. And I know this all sounds a bit crazy. I'll show you later an example in practice. But this is the bit where the user prompt can be enriched with the context of your own internal data that then gets handed over to a large language model, which then can answer not only on the basis of its own pre-trained data, but also on a larger prompt that includes already relevant information, and then it can give back to the user either instantly a response, or it can even call internal functions and APIs, which is also quite helpful, right? You might have a writer team that has already created content in quality, but might have now to do the chore of writing a lot of different stuff. You can have them basically generating smaller conversation on the basis of their own work already, and can really augment their work. And I'll show a bit later about that. So I promised you a demo that this is not just all completely abstract what I'm talking about here. And so at ActionC, we built a small tool that uses seam carving to resize store assets. So imagine we have to now got all the key arts from our artists, and what is the worst thing that everyone has to deal with is now we need to resize them and make them ready for use with Steam or the Epic Game Store and all this. And let me show you here an example. We have here our key art, and I fed this model with the documentation from Steam and from Epic on what measurements they need for the store. So, So let's do this and then submit. So while this runs, this should take about 30 seconds because I'm running this here locally and it's not very optimized for CPUs. Basically, we're using this library called LangChains, and we're using from Hugging Face a model that is, again, optimized for CPU use. We have given it PDFs, which is basically just a download of the websites where Steam shows all the different asset dimensions. It will process these PDFs. And now comes something I found incredibly crazy when I worked with this stuff is we're basically prompting now the model. I have just given into the model, I want a page background. But what happens under the hood is the model now needs to have better instructions. So I basically beef up what the user puts in as a prompt with more data. And this is what happens with these briefs. And I found it quite crazy that as a programmer, now you're using this kind of instructional language to a model to explain it what you want it to do. Right? So you tell it, give me a JSON with key width and height, which then basically our other function that it's calling uses to resize the asset. And you can see it used the 1438 by 810 page background. Yes, so it was successful. Right? So the large language models are quite good at just processing unstructured data. So you could imagine now I can just pop in more and more and more of these PDFs, and my application is instantly ready to resize for these different requirements. And that is just to show you, this is about 1 week's work by our expert. to put this together, to test with the different models, and you have something that can take a chore out of your team. Yeah? Great. And yeah, so what happened there? Oops, I need to go to change the window here. So application UI, that is something that I found also very helpful. You don't have to bother with all this, creating a front end and have a separate development string on this. You can use these, it's called Gradio or Streamlit. You put them straight into your Python code. You can instantly share them. You get a share code, a tunnel to your own machine, or you can upload it here to these specific spaces, Hugging Face. Instantly, your app is accessible by your team. Right? It's very fast, very cheap to test and play with these. Oh yeah, you containerize it in Docker, as you know, and then just run it in your own cloud. Good. Some more actionable ideas, how you could use this. As I mentioned, open world NPCs, I would imagine for writers, this is a major chore if it's not for the few VIP characters. But imagine your team created the lore, it created the setup, villages, etc., the big bios, and then now the machine could just roll out more and more content when people want to approach other characters. Then player personalization is another big topic. Give a lot of context data of what your player has achieved, what they've been doing in the game, and then you can dynamically adjust. Which items do they get offered? Would they maybe get any specific tips, help, etc.? And then don't forget the other teams in your company, right? There might be HR teams, there might be people who get often inundated on documents that have been created. You can almost build your own internal chatbot that can use your own data to answer frequently questions, etc. And yeah, this is us. I want to say thank you to the people that enabled me to learn this technology, Jeremy Howard and Shabnam Bashir, who has worked as our ML consultant, and then obviously the open source community. And this concludes my talk. Thank you. So I'm now happy to answer any questions if you have the mic.
First of all, thank you. Amazing talk. I learned a lot. What do you think makes machine learning biased?
What makes the bias?
Biased, yes, like with Gemini, the case of Gemini.
Yeah, I think a lot of the bias comes from the quality of the training data. So I think the beginning of what these models have been trained on was already by nature what was data that was available to researchers, right? And that had probably the usual biases that also we are aware as our industry, right? So like there is more, it's more male leaning, it's probably more white people leaning, et cetera, right? So these biases, I think, drag through. And it is also a good reminder of why I believe we need to be having these tools in our hands and use them in an open source and in a broad context, because that will the best attack these biases and make sure that, you know, the more of us using it and the more we can address that, right?
Hi there. I've got a question around one of the use cases you had about personalizing the player experience.
Yeah.
What I understand today when I talk to a lot of game developers is they're already using traditional ML to do LTV, fraud detection, blah. How do you see, or do you see an opportunity to use more unsupervised learning using neural networks for that portion of making money in games?
Yeah, I think if it comes obviously to the money bit, and the more harder you want to control the reward and effort systems, you might want to have a more traditional analytical use of your models. Nevertheless, I would imagine as well you could use it for how content could affect the engagement, right? Would maybe your NPCs in the game speak more supportive, tell the user a bit more hints and tips, so you could affect it in a maybe a bit more, I would say, soft manner that is maybe not as obvious as saying, hey, here's the offer X, use that now, and we've adjusted the price because we believe that's what you spend next. So I think it can work in good context, but yeah, handle with care, right, to give an LLM these functions. Okay.
Hi, and thank you for the talk. It was very nice. Quick question on the vector space topic. I assume it works this way, but you had the conversion from king to prince, right? Is it as simple as the conversion for prince to king is just the inverse of that function?
It should be. Obviously, this was a very stark simplification, right? We're talking about vector math on the length of about 3040 vectors now in GPT. So the math is a bit more complex than that. But in principle, yes, it's that this navigation of the space and its similar principles allow to navigate the meaning.
All right, thanks.
Oh, sorry, you just ran off. Sorry.
Yeah, just going on from what you just said about the size of the vector spaces that the big models are using, where do you see the limit hitting? Because are we slowly getting towards, like, for training and stuff, are we slowly hitting any?
Very dangerous. I'd say probably before lunchtime, I was safe what I just said. It's an incredible fast-moving space. I think there is a lot of optimization around how can the compute effort be taken down, right? A lot about how can the memory size reduced. It's just an ever-moving space, right? We don't know. You'd see one paper in 2017 just unlocked all of that. Who knows what they come up with next? There is one topic I currently see, which is to move the value, the activation functions, away from the neuron and rather put it to the connections. So that's called the CAN. Again, I don't know what will its impact be, but that's also what makes it so exciting, right? It's a field that is still very accessible and still unlocking big efficiencies. Right? It's not like any other things that are very established techs yet. Cool, thank you. Good.
Hi, thanks very much again for the talk.
Pleasure.
2 questions. Will you be making the source available for any of this, to the simple example you showed about the cutting, or might you show more of the LangChain part? Specifically, I'm curious how you integrated calls to, you said about the cutting, etc. I had a little look at it, but I didn't get that far. So just curious to hear your thoughts, your experiences, maybe also limits.
Yeah, just meet me afterwards. I haven't planned to make it open source, but yes, just see me. I'm happy to share. At you. Great.
It gets asked every AI talk. I've already been to 2. Stigma associated with AI usage with the public, etc. How do you balance the enthusiasm, etc.? Any thoughts on this? It's always interesting to hear people's opinions.
Yeah, I think that's, I can only speak about my own philosophy, obviously, right? I think it's important, again, to use it to tackle chores and look at, obviously, how do we assist our domain experts. I think it's a fallacy to think that there will be no artists anymore in several years, or there will be no coders anymore because machines program themselves and we all just put prompts. I don't think that will happen, right? And another thing is, for me, truly this, make it use on a broad basis. Let us get our hands on it, right? If you leave it to big tech, the disruption is probably more of a risk than if we say, what can we do with these tools in our hands? What can we make, right? We're gamers. We use new tech to make better games, and it should stay like that. Right? As soon as we start to give in on to the conflict, I think we will miss out on the promise of making this a better work environment for us all. Yeah, and make the machine do the boring stuff. Right. I think that's it. Thank you very much. Glad to see you.